mathematically, a population catastrophe happens when A is greater than 1, because it means that this population is going to have a vertical asymptote at some point. In other words, that this rabbit population is going to blow up to infinity. It's called a catastrophe for a reason. Naturally, biologically, that doesn't make a whole lot of sense. We could not support an infinite rabbit population in any ecosystem. But population biologists are clever people, so they like to call it a catastrophe, because that's what the mathematical model would predict. So a couple things happening here. First of all, you're given data in the beginning of population versus time, where population is measured in thousands. And then the first step is to take those population numbers and turn them into rates of change, dp/dt, using a symmetric difference. So let me just pick on one of these numbers, and group that worked on question 5, let's maybe pick this one right here. How did you compute this average rate of change using a symmetric difference at time t equals 3 months? Where'd it come from?
We subtracted 5.10 from 2.5.
Okay. You got 2.6. And?
Yep, and from 6 minus 0.
6 minus 0.
And then divided p by t, because the rate is dp/dt.
There we go. So over the months from t equals 0 to t equals 6, that is a 6-month time difference. And the population difference over that period of time is 2.6 thousand rabbits. And so the rate of change is 2.6 thousand rabbits divided by 6 months. That's 0.4333 thousand rabbits per month. Right? And remember, when you're doing a symmetric difference, you're looking at the left and you're looking at the right, but you're not looking at the point that you're at. Right? So that removes the bias of looking forward only or looking backward only or looking both forward and backward. So that third row of the table, as you've helpfully noted in the margin, comes from the symmetric differencing of dp/dt. Okay, but then we were interested not just in those numbers, but in the logarithms of those numbers, because after all, as we said in the last problem, this population rate equation can be linearized by taking the logs. In this example, the natural log, dp/dt, equals, and just skipping the steps because we've already done them in the last problem, a times the natural log of p plus the natural log of k. And that suggests that the variables natural log of dp/dt and natural log of p linearize this rate equation. In other words, the natural log of the rate will play the role of our y, the natural log of the population itself will play the role of our x, and that is why, in this table, those are the last 2 rows. So how did you get the data in those last 2 rows?
You just put the values and evaluated them at whatever they were. For example, like we evaluated the natural log of 3.46, and we got 1.241.
Right. So just taking the natural log of the numbers in your data table will fill out the last 2 rows of that data table. As you say, plug and chug. So of course, we're still interested in figuring out whether these rabbits are catastrophically populated. In other words, if they're growing at such a fast rate that the mathematical model would predict that they would blow up to infinity. Not blow up like explode, but blow up as in overpopulate, let's say. So in part B, I just asked you to plot the data points, the transformed data points that you found in part A. And so you plotted them. Here they were. Here they were not. But here they were. Yeah, I've got to give you a hard time. All right, so then the question is this a catastrophic population? And that's part C. So let me ask, what did you do here in part C?
Using values that we got from the table, we did the slope of y2 minus y1 minus x1.
Okay, the rise over the run. 2 minus x1. And let me ask about that choice. Why is the slope of the y versus x relationship going to tell us whether this is catastrophic population?
Because when you linearize the equation, the a is your slope.
Exactly.
Or the n value.
Right. So we're looking at our original equation, and we're saying, well, I want to know what value this exponent a has. In our linearized equation, that exponent a happens to exactly be the slope of the relationship between the log of p and the log of dp/dt. And so they said to themselves, selves, if I want to know the slope, I better find a. Sorry, that was backwards. Selves, if I want to find a, I better find the slope. And so you found the slope. Using the data in your data table, you took the rise divided by the run, and ended up with this number, 1.5799. And you made the conclusion that we are in for a lot of rabbits. It's a catastrophically growing population because this number is greater than 1. The only quibble I have with what's up here, and whether or not it's a minor quibble depends on how I feel when I'm grading your exams. But let's talk about it just in case. The quibble that I have is right here. Whoops. The units that you've written down here for this slope. Can anyone tell me why I don't agree that the units of this slope are thousands of rabbits per month? What variables is this slope relating?
The natural log of p versus the natural log of delta p over delta t.
Indeed. So this slope is relating the natural logs of p and dp dt together. Let's take those one at a time. What are the units of the natural log of p going to be? P is measured in thousands of rabbits. What is the natural log of p going to be? You may think of this as a trick question. It is not, but it may sound tricky.
The natural log of thousands?
The natural log of thousands of rabbits?
Too simple?
What happens to units when you take their natural log? They go away.
Oh, yeah. I just guessed.
Yeah, that's a good guess. The natural log of p is dimensionless. What about the natural log of dp dt?
Also?
Also dimensionless. There we go. And so that means that this slope is also dimensionless. That this exponent, after all, this a is really an exponent in our original equation. And exponents always must be dimensionless as well. So the slope of this is 1.5799, and it's a dimensionless quantity. Now, we could take that 1.5799 and interpret what it means. In fact, let's do that just to tie a bow around this whole problem. What is this 1.5799 telling us? 0.5799. And that's a change in the natural log of dp dt per change in the natural log of p. So when I go plus 1.5799 in the first, I'm getting plus 1 in the natural log of p. So every increase by 1.5799 in the natural log of dp dt corresponds to an increase of 1 in the natural log of p. Okay. So again, we're in the situation where we've got the logs of quantities increasing. How can I rephrase that to tell me something about how the quantities themselves are increasing? Let's take the natural log of p. When the natural log of p increases by 1, what does p do? How do I get rid of the natural log in this equation? If 1 is equal to natural log of p, then what's p? That would be for a base 10 log. Here we have a base e log, right? So take both sides and make them exponents with a base of e. And we find out that when the natural log of p increases by 1, p increases by e, but not just by e. Remember, when we translate from linear to logarithmic, we exchange multiplication for addition. So we're talking about an increase in the population by a factor of e. And e, remember, is just some number, 2.718281883, ... So just a number, whatever. So when our rabbit population increases by a factor of e, what happens to its growth rate? How much does it increase? Again, when we trade linear for logarithmic, we get a factor of, and what's the factor? It's e raised to the power 1.5799. So when the population goes up by a factor of e, the growth rate goes up by a factor of e to the power 1.5799. So that little interpretive step, this is the one that I've clubbed you over the head with now a few times in the last week. Hint, I'm probably going to club you over the head with it one more time, because I have you for another hour and a half. Expect that you will probably see this once more before the course is over.